This video is going to show you how to combine the conservation of energy in a perfect world with the work done by non-conservative forces in the real world. So a 1001 kilogram car is traveling at 22 meters per second when it applies the brakes for 10 meters and slows down to 14 meters per second. How much force is applied to the brakes? So I've got this already diagrammed out. I've got a little rectangle, so that's my car, real fancy car there with a block. On the left, it's traveling at 22 meters per second. It moves for 10 meters so it gets to the position on the right, where it's traveling at 14 meters per second. And across this entire 10 meters, it has a resistive force that I'm trying to calculate. So when setting this up, I need to pick my two locations. I'm going to pick the beginning and the end because I know the speeds, I know the heights at the beginning and the end. So I'll start by summing up all my energies at the start, and then in this case, the force and the displacement are in opposite directions. That means that the work done by this stopping force is removing energy from its initial position or initial state. So that's going to be minus the work done by the brakes, and that's going to equal all the energy that I have on the right. So I'll sum up all the mechanical energies that I have on the right. For my summation of energies, I'm going to look at the kinetic energy and the potential energy due to gravity. Then I'll subtract the work because that's what I did above, just leave that alone. And then on the right hand side, where it's 14 meters per second, I'll just add the kinetic energy and the potential energy to gravity. Now, that's my generic formula. I need to figure out which of these energies I still have in order to put my equations in, so I don't, to identify all the energies, where the energy is flowing. So what I'm going to do is ask a couple questions. I'm going to start by looking at the location at the starting point on the left. So I'm going to ask, is the car moving at this location? In other words, on the left. And in this case, it's moving at 22 meters per second. So since it's moving, I'll keep the kinetic energy. If it wasn't moving, I would get rid of the kinetic energy in my next step. Then I'll ask the next question, is it above the other location's height? In this case, it's not. So this is a low point. I'll call the height 0, and I'll get rid of its potential energy due to gravity. Now I'm going to look at the other location where it's traveling at 14 meters per second. And the question I'm asking are the same two. Is the car moving at this location? Yes, it is. So I'm going to keep the kinetic energy. The next question is it above the other location? And it's not. It's the same height, so the height's also 0 there. So that's going to go away. That's going to leave me with 1/2 mv squared minus work equals 1/2 mv squared. But I'm not going to leave it as work. In this case, I'm going to replace the work with force times distance because I'm looking for the force in this equation. Then I'll plug in all my numbers in my variable, and I'll solve for the force, and I'll get the force at 2,320,000 newtons.